Welcome back everyone. Now we are going to learn about D flip-flop. So let's start with its design part. And what we need to design here, well, let's configure first that what are the things that we require. So we need three AND gates for this and two NAND gates for this. Well, when I first read that thing, one thing came in my mind simultaneously. You may ask, what? Well, oh, can you tell me that why we need another flip-flop? Like you just shown us here, that it's D flip-flop. So that's another kind of the flip-flop. Why we need that? That's my question. Well, excellent, my dear friend. You are asking the question, so I am here responsible for the answer. So let me write that, and along the way I will explain that why we want D flip-flop when we already studied this much extensively about the RS flip-flop, and we already know that what a flip-flop do. So why not just one flip-flop and that's it? Well, the reason is, in case of RS, in case of RS or SR, whichever way you like to call it, that we studied flip-flop, when R and S is set to 1, is set to 1, the output that we have, outputs Q and Qn plus 1, actually Qn, technically Qn and Qn plus 1, that's the output we were having. So it becomes 0, right? Becomes 0. Well, this is something that you need to look carefully. That violates actually something. That violates the rule. Well, which rule you may ask? The rule that the output Q and Q dash. Well, I'm writing Q dash. You may understand this like presenting Qn with Q and Qn plus 1 with Q dash, the next state one, are the complement, are the complement. That means it's reverse. If it's 1, it becomes 0, or it's 0, it becomes 1. This way. So, to avoid this, to avoid this condition, avoid this condition, D flip-flop is introduced. D flip-flop is introduced. So that's how we are using the D flip-flop. So did you figure out that why and what was the problem with the SR flip-flop? Well, in the SR flip-flop, when both are set to 1, as we seen here, when both are 1, like in this case or in this case, we were having two conditions here. So just see that these two cases, S and R's value are the same. As you can see, S and R values are same, but the states are different. 0, 1, and in this place it's 0, means no change, and in this place it's 1. So how can, in which world it's possible that you are giving S and R as the input and 1 as the clock? Then you are getting one time 1 and another time it's 0. Well, That's not fair, right? That's why we introduced and solved the problem by introducing our most appreciable D flip-flop that will considerably solve our problem. Well, D flip-flop is introduced in which only one input, it could be higher or lower, but only one input is needed. One input is needed in D flip flop. So no to input, no problem. As we can only have high or low. We cannot have the both or that kind of the conditions. That is what we are trying to ignore. And this is achieved by 3 AND gates and 2 NAND gates. Now we can proceed to the design, but I hope you are getting excited and you understood completely my point of view that why we took this thing. Well, first reason is that in SR flip-flop with the clock 1 and S are both 1, it is giving two possible outputs which is not technically possible. Second thing is in SR flip-flop, if S is high and R is low, it is not a good balance. We want a simple logic that it's high or low. That's it. That's all we want. So, because it's the part of the same thing, you cannot just tap into a folder, like you cannot just tap into a folder and it will open and close at the same time. Well, in when our file gets corrupted sometime it happens, but remember it cannot open and close at the same time. So we either want it open or we want it to be closed. So to ignore these conditions we require one at a time. That is given by D flip-flop. I hope the idea is clear right now that because of the open and close at the same time. And what are the flip-flops? Flip-flops are just memory, and what the memory is going to do? Memory is going to replicate the actions that you are going to perform. It will going to show you up from your register, and that will going to give the command for the processor that will upload it to the RAM, and you are able to see that all the things. So it cannot be open and close at the same time. That's why it is required to have just one at a time. That's the use of the D flip-flop. Well, now let's proceed to his design part and let's design our D flip-flop. Well, to design our D flip-flop, we just need one input. So let's make our one input first. This is the D, which is our one input. And now here we are introducing our first AND gate. And now we also want the clock. So let's make our clock. First of all, let's make our all AND gates. This is one of the simple practice that whenever you learn it and you have to make it, just remember that how many AND gates or NAND gates you are actually using. That's all what you want. Because once you learn that and perfect that, you can make the connections easily. At least it becomes a little easy to perform certain actions in various practices. Okay, so we are done with it. So here what we are going to have is going to called as, at this point we are going to have Q, and in this point I am writing Q dash, two things. Now it's time for the connections, so let's connect everything. So I'm connecting it here. Surely there is just one thing, so I'm connecting it with the input, as it can only have one thing, right? And now it's here, and again this is going to be here. Let me redraw it. Okay, now it's perfect. and this will going to be here. Well, don't get confused, this is AND gate, okay? It seems like a little bit NOR gate type, but this is AND gate. I will also write that, okay, in just a while. Alright, so now we need to connect these two also. So I'm connecting this with Q dash, and I'm connecting Q with the input of this one. I think we are done. We just require a clock, so I'm adding up the clock here. So this will gonna be our clock, CLK clock. So when I say which one I'm talking about, it becomes confusing. So for that, I'm just writing the number so that we can understand very easily. Whenever I try to figure out that we are talking about 3 or 4, you can just look at it very easily. So this is the thing, and we are done. So this is our NAND gate, this is also our NAND gate, and these are our AND gates, AND gate, AND gate, and this one is also our AND gate. Well, here you can notice that there is only one input, rest everywhere there is two inputs, and we surely have two outputs too, which is giving the feedback. Well, feedback, and that feedback is becoming the input for the second that is coming from the first, and input for the first that's coming from the second. Well, that's the advantage. The feedback is the advantage that we get, and the things can perform in a great way, and things become easier in this way. So this is the diagram, and that's how we just introduce our D flip-flop. So congratulations, my dear friend, you just learned the design of D flip-flop. Now you can just buy a few AND gates and NAND gates and just connect it with the circuit, just one clock, and you are done with it. You are done with designing the D flip-flop, and you just solved the problem too. So let's make it truth table and understand its part in the logic way, because this is the logic but this is the design part. So we just designed our thing. Now what was the requirement, or what can it solve, that we are going to see right here. So first thing first we need the clock, then we need the D, and then the states Qn and Qn plus 1. Well, as in the diagram I wrote this Q dash and Q, so don't get confused, this is the same thing, okay? Okay, my dear friends, now let's make it. Let's make the magic happen. So here we are going to learn something very interesting. Let's fill it up. So we can have the zero state. For the zero state, D flip-flop is not active. We have no QN, and here we have no change. Well, I can also write that it's not performing, but I don't want to write that. I don't want to put the cross. I want to put the no change here. I will tell you in a minute that why I did so. So for the 1, we have 1 and the 0, and here we have 1, so the state is changed, and then 1, and then we again have the 1, then 1, and then 1, and then we have our 1 0 0, and then we have 0. Well, then we have 1 0 1, and it will going to give us the 0. So if you look at closely, we have covered all the 4 possible combination. You might ask me that Why I just don't wrote it in this way, that 0 0 0 1 1 0 1 1. Well, you can do so completely, it's completely fine and fair. I just twisted it a little bit. That's it, nothing special. Just to conclude few things quite easily, that's the whole point of it, nothing else. Well, so let's start with this one. So the D flip-flop solved our problem, and it's giving us the truth table. And now we're going to figure out that what's gonna be the next. Well, in this case that we have in here, when the clock is inactive, as you can see here, that the clock is inactive. So the D is inactive for sure, the Qn is inactive, and Qn plus 1 is no change. Well, it means something. It is stored value. It can store a value and keep it. When you change the clock cycle, it can change, but for now, it's no change. That's the whole point. I have not written it inactive or the cross thing. I wrote it no change. That's the whole point of it. Okay, now let's study this one. For every of the next thing, the clock is active, so we are not going to focus on clock anymore because it's remain active. Now, for let's start with the 0 0 case. That should be technically the first one, but I twisted it a little. So 0 0, it means the D is 0, means input is 0, so output is 0, and the next state is also 0. As we are using the and NAND gate, so the point is that it will going to be 0. Okay, we will also see that in the diagrammatic form, but for now it's just a 0. Now, when we have 0 and 1, what is there? Well, remember, my dear friend, why I have not written it in this way. I can write possibly, but the main point is this is the only input. If you look closely, that was the whole purpose of drawing or designing this thing. This is the only input we have. So what are these things? These are the outputs, and these outputs are actually providing the input signal for the next state and the previous state. It is affecting each other, but still they are just the outputs, and we are only having one input. And you can if you consider the clock as input too, well, you can consider two inputs, but the clock, as we know, it's not varying much, just a 0 and 1 state. So if you look closely here, we have two ones and two zeros. That's it, that's the whole point here. So it's either active or inactive. So in the inactive case, if the Qn, you store Qn as 0, it will going to remain 0. If you in just another way, if you remain make it 0 and the output is 1, it will going to invert here. That's the point. Previously it was not inverted, but this time it will going to invert. Well, it is going to invert, and that's the point I wish to make. And here it's not inverted. Now this is 1 1 1. It means no change. Actually I wrote it here, but the thing is the states did not change. I mean with this one, let me change the color so that I can highlight it fully. This one and this one actually did not change. That's amazing, right? D is going to remain active for next two ones. Now when this is gonna be 0, this will gonna be 1. So in this case it's inverted. So as you can see, two times it's inverted and one time it's not inverted. That's the whole point. In this case it's inverted, in this case it's inverted, and in these cases it is non-inverted. Non-inverted. You may ask that why it is so. Well, we designed the circuit in such a way. And why just 4 combination, not 5 or 10 or 50 or just one? Well, the whole point is to make the thing accessible. Like you want it to be open, So you also want it to be closed, whichever way you want it. Just imagine if you open a file, and in that file you just made a few changes. You changed the thing and you named it file 2. Now you want it to remain file 2. That's the first thing that happens when you save as. But just imagine that if you don't save as and you opt out, that you might have mistakenly did something but you do not want to change it. So what will going to happen if you don't save as? If you don't save as, so what will going to happen? It will going to remain the file and not the file 2. Okay, so that is the whole point, my dear friend, that one time it changed and the another time it did not changed. This is the point. So this is going to be highlighting point for the save and save as. Well, every bit of the programming and whatever we do is having deeply connected with the digital electronics and its designing system. It's flawless. That's why it's working so smoothly. And when I am saying flawless, I mean theoretically absolutely flawless, and practically it's working very well, very well. So that's the whole point of using this all the things. I hope you got the point and you have reached to a point where we can learn about the next interesting thing, which is our JK flip-flop. So what say, let's learn the JK flip-flop. So in the JK flip-flop, what does it do? Actually, this flip-flop is the refinement of RS flip-flop. Well, surely the RS flip-flop is developed, so we just refined the thing. JK flip-flop, as we can see, there are two inputs that's gonna be, and not just one input as it was in the D flip-flop. JK flip-flop is refinement of RS or SR, whichever way you like to call it, SR flip-flop. So what kind of refining it has done? We need to see that, right? So um, which condition were we most excited about? It's R equal to 1 and S equals to 1. That was the problematic part for the thing. Now it's designed, the JK is designed in such a heroic way that it solves that problem completely and forever. So let's see how it's working. So first thing first, let's see its design part, and that too is very easy and not complex. That's why I like it. Okay, so let's design the circuit. So the entire circuit is designed with two AND gate and two NOR gate. That's all we want. Just four things, nothing else. So let's just make the gates first. This is AND. This is another AND gate. Now I am just drawing the NOR gate, and this will gonna be the second NOR gate. And now let's just give it the connections. So here we have K, and let's say this is J. Well, you can invert it, it will not make any difference. I'm just writing J below and K above, will not going to make any kind of the difference. So this will gonna be the clock. Well, this is similar for almost everything. So this will gonna be our clock. And what else you want? Well, now the most interesting thing is started happening. Let's connect it to the next level of it. Now this will gonna give the input for this one, and this will gonna be giving the input for this one. So till this point everything seems quite normal, right? Now the interesting part comes over here when we start making it. So this is Q, and let's write it Q dash. So what is going to happen? Well, what I'm going to draw, you will just say that it's the same thing. Well, you are not completely wrong. It is indeed seems same as RS flip-flop. It is giving the feedback that we also received in our SR flip-flop. So why this new thing actually came? Well, this is gonna be the interesting factor that I would like to mention. Actually, I would like to mention this point, and let me just remove this part. I will show you that why I removed it, and also this part that I want to redraw, and I'm gonna connect it again to this. Now this will gonna be the Q. So this is Q, and surely this is Q dash. Well, this is not the circuits part, so I'm removing it. Okay, so now this will gonna give the input for this one. This changed everything, literally everything. So what I meant with here, okay, let me make it clearly so that you can see the things quite enthusiastically. Well, I'm just improving my drawing skills, nothing else. You can try and practice that too. I am just trying to make the straight line. That's the whole point of my drawing again and again. Well, so this is the thing. Well, we have feedback here and here. On that feedback, the entire input is gonna change. That will gonna change the output itself. Remember that if you are having time machine, yes, it is theoretical, but if you are having time machine and you can just go and reach to the starting of the event where it actually began, and you know that it is having some flaw, and you correct it to that very place, these very places. So what's going to happen? Well, there will be no flaw. That's it. There will be no flaw. That's all what we want. Flawless system. That's the entire point of it. If I allow ourselves to compare it with the SR flip-flop, so as you can see, there is not much difference to AND gate and to NOR gates. We were even having these feedback things here. So what was it? Well, we just did this thing. Can you imagine that this thing was the refinement? Well, when I first read that, I said, why not? It's done in the RS itself. But as a teacher, now I have to tell you the reality. I really don't know why they don't do that in the SR and call it SR itself. Now we are studying the JK flip flop, so that's the whole point of JK. And now finally let's make it truth table. Well, you already got its point, but still it's my duty to teach you the truth table so that you understand all the conditions without having a single cent percent of the doubt, as you're studying with me. So doubt, well, no chance, right? So we have to eliminate all the kinds of doubts, and we will work on the basis of the logic that will going to take us to the next level of our learning. Okay, so let's begin with this. So first of all, it will going to be 0, and as usual these were going not to work, right? And this is going to be qn, it means no change type condition, right? Now you have got my point. And now just 1, and if you keep it 1 and 0, what will going to happen? This will going to cross, and this will going to give us 1. Now I'm going to amaze you. Just keep watching. 1 0 1, and this is cross, and now this will gonna be the 0. You want to see the next one? 1 0 0, this will gonna be cross, and this will gonna be qn. And now again 1 1 1, and this will gonna be cross, and this is gonna give us the qn. That's the whole point, my dear friend. Now you know that why I focused and emphasized and convinced you even that why we should learn the thing which is called as the truth table, because it speaks the truth no matter how much harsh it is. As you can see, there is no importance, don't care condition is occurring here for the qn. Well, the cross is the don't care condition. It means we don't care it's 0 or 1. So it's does not matter. But physically we have to implement it. That's why we write that. But actually, as you can see, it is not going to make any kind of the change. No change. So actually, this is useless. Only this is gonna be useful. Means one output is valuable for us, is valuable. Now you can see that what the thing our scientists and digital electronics engineers have done. Well, in the D flip-flop, what we were having is one input and two outputs. Now the problem is reversed, and we made a new thing which is called as JK flip-flop. In this we have two inputs but only one considerable output. The second output is just working for giving us the feedback. Yes, it's not idle, it's not idle, whatever way you like to call it. It's not free. It is giving the feedback. The Q is giving feedback back to the K, but the ultimate thing is it's useless for us. Logically, it does not make any sense. So, while making the table, we can see that it is not even participating in this. So in these two cases, we were having Qn for these two same conditions, right? And for this one, we already solved this problem two times, and this is the third time. Well, first in the SR flip-flop, second time in the D flip-flop, and this is the third time. So 1 and 0 is already solved. So for the J1 we are going to get the 1, for J0 we are going to get 0. So you might say that what the K is doing. Well, K is busy talking with Qn and it is confused. So no matter 0 or 1, it is not making any change. Practically it's making the change, so don't get confused. I am just saying it in the joke form so that you remember it for longer term. It is present. We are listening to qn, we are listening to k, and we have our big ears that is listening. But the thing is, we don't care. We don't care whatever is coming from qn and a. They are giving the feedback, they are making the circuit complete. That's why we are studying it, but we are not caring that what's going on. That's it. That's the whole point. And the qn is present in both of these places. For the 0 0 it's qn, for the 1 1 it's qn, means the previous state. Well, I would like to tell you one thing that I have learned by my tricky mind, that if you consider it as the present state, so just consider qn plus 1 as the future state or next state. So what was the problem with the SR and the D? It is trying to predict the future, but what the JK did, it said whatever deeds you have done, or in Hindi we say whatever karma you have done in your past will going to give you the result for your future. So this is the present and you are going to get exactly what you just did. Nothing else, nothing new, nothing old, just the same thing. That's the whole point. And that's the way we learn the JK flip-flop. I hope you have enjoyed this journey of JK flip-flop. Now we are going to learn just two more flip-flops that is solving various problems, but we have just solved the SR and JK flip-flop problems and the D flip-flop, and we also learned a little bit the life philosophy that how the future is unaffected, or you just already know your future. Whatever you are doing right now, you will learn that thing. Like right now you are studying with me, so after some time, after one or two revision with conscious mind, learning, effort, that will be your future. You know that all the things, you are master of this thing. Well, this small teeny tiny little of the things, when we add these all up, it becomes wonderful journey. So stick with me, take care,